So if I define a structure like modulo prime number, then I should be able to have algorithms for addition, multiplication, so that I can use it for like a phi field. Okay. So now I have another set of slides which have been given to you on the proof of that matter, but before going to proof I thought maybe I will explain this to you, so you all can see, yeah. So so far what we discussed is a modulo a prime number, right. So on this is a Magma is a software developed by University of Sydney, and it's Australian product. It's been used world over for finite field applications, and whenever you want a finite field, for example with the coding, I will give some examples that, so if you want to understand more, it may be easier to work with this software rather than. So for example, I want to write numbers like this. I can say now ZP I can define like this. So maybe let's for the P equal to say 31. Okay, and I can ask this question like is prime, then it will say in this case and say submit here, true, it can tell, right. And you can also, like for example, then is the prime number, so I will put say Z31, I can put to like this is I can say integer ring 31, or maybe the prime in this case P. Okay, and I can ask what is that 31, okay, and submit here, it will return a residue class of ring of integers modulo 31. So what Magma tells you, you give an object that is Z31 that has all these elements. So as I explained to you last time, when you consider modulo 31, we are not really looking at numbers, they are actually residue classes. So each 0 there is all the numbers that is that gives 0 after multiplying by 31. One is, so each one is a class. Now object, what this software gives you is a Magma, the object of that. So one of the simple thing that you can write in this case is like say you have 31, so for I in Z31 do I and for, you can put, it will actually list down all the elements. Of course I have to run here, submit, because this is an online version, so it runs things. I'll just show the result. See, it goes all numbers up to calculations are restricted 100. Why it's not giving? Okay, see here. See 31 up to 30. Okay. So now the other concept is, okay, I'll remove let's keep it here. I'll remove this code. Let's take an example of the GCD algorithm that we talked about. Let's take say a number like GCD. You can put GCD of between say number, you give me some 25, 31, and just say submit. Yeah, so it's 3 residue and the GCD is 1, right? That's clear. Now I told you that in an extended GCD algorithm, given 2 numbers, you can always represent it as linear combination of GCD can be represented as a linear combination of that numbers. So I will demonstrate to you how that can work. So for example, instead of GCD, I will now write XGCD of 25, 31, then go here and submit. So you get what the XGCD tells you is that given, so A, like say we gave in our XGCD definition A and N, right? Given A and N, it comes up with 2 numbers X and Y such that, so you can see that 25, the first one is GCD, second two numbers are x and y such that 25 times 5, 31 times minus 4, if you add them you should get the GCD. Now just look at it, 25 times 5 is how much? 125, 31 times 4, 124, and it is minus. So when you add it you get 1. So it is always possible. So given a prime number and any number less than that, if you run through this algorithm you will get two numbers that the GCD is represented as. Once I have it here, so I want everybody to understand this, and so that we can easily relate to our course later, and it becomes a pretty useful concept that you think. So what I did was basically I did XGCD, that is extended GCD algorithm. So the next set of slides you have is basically to show that extended GCD algorithm indeed works, and whatever the output, the GCD it gives is indeed the GCD, and you can prove it, and it is a theorem proving version. So you need a bit more time to go through it. So let us see, what I do is I take it as an exercise, go home today and work through that, and if you have any questions about it, like someone asking, we can discuss tomorrow about that. Yeah, but to, let us say we need to do so many things, so to go leap forward, it is better to learn through examples. And one of them is the Magma. You can always, I can share the link, you can go and work on the internet yourself. So this XGCD gives now an example is here is 25, 31. What it gives is that GCD is 1, that is 25 times the x happen to be 5 plus 31 y happen to be minus 4. Okay. Now this equation holds true in integers. That means these two numbers gives is in z integers, right? You all know. So now what I do is that now I take mod 31 on both for this equation. I now take the residue class of like apply the modular arithmetic on it. So when you take mod 31, so the left hand side 1 remains. Now rest you get 25 times 5, and what happens to this? This is 31. So any number which is a multiple of 31, if you divide by 31 you get remainder 0. So mod 31 is 0. So what I got was that 1 is 25 times 5, so which shows that 5 is the inverse of 25. So if I have an XGCD algorithm, let us say given XGCD algorithm, can you write your own algorithm for inverse of a number? So how would that function would inverse look like? Can you think of? So first what you do is you write function, take that input as a comma n, okay, and first thing that you do is give XGCD of algorithm, so it gives you x and y, return if the GCD is 1, return x. So you get the so by using XGCD algorithm I can easily compute inverse of a number. So now we had an example last time with the modulo say 31. I take now a simple example. You have a 0, 1, 2, 3, 4, 1, 2, 3, 4. Now I can fill up, let us say if I want the multiplication, I can fill up this particular table with the results by taking multiplying modulo 31, and across also you can have addition modulo 31. You will see that for with multiplication any non-zero element you will only see 1 and any one of the rows. That tells you that the inverse exists. Now if you want to really implement inverse, now I can write an algorithm pretty easily come up with that, correct? Is that idea clear? So in fact the set of slides that I gave you for the things is basically proving that in a theorem proving fashion, okay? So I think it's better to you go there and take this home and come back with the thing. So we know how to now write inverse of a number, correct? Yeah, and the simplest structure we use modulo prime. Okay, so after doing that, so we will go through next set of our slides for the day. So this is the kind of we had a little gentle introduction to coding theory yesterday, but it was probably too gentle. So we will start with a little more things in the binary codes. So here I will go through some general model, and some of the things may be already familiar to you. So first I go through some introduction and then introduce communication model where error correcting codes are meaningful, then some definition of codes and binary linear codes, some bounds and application, but we will probably go through bounds in the next class. So as I told you, the topic of error correcting codes, see, remember that today already you give you some idea about how the storage works and RAID technologies you saw, and most of the cases were like most of the technologies were invented mainly from the idea of easy access, and so the codes used was pretty simple. In some cases no code, in some other cases it is just repetition. So repetition itself is an idea of a code we will see through in a simple way in this lecture, and the repetition code is an important class of code, and even though it is a trivial code, we need to understand the proof and other stuff in that. But then so as we go through higher things, so we will have to make connection between these two and move on to the things in coming days. So here this was a major as a solution. So mainly error correcting codes are used for in the communications, digital communications, and I already gave you about the emphasis in the first lecture. So as you can see, this is a kind of thing I put up. This is who know about G.H. Hardy? Do you know G.H. Hardy? Anyone who doesn't know G.H. Hardy? So at least I want people to raise hands. Yeah. So G.H. Hardy is, so you probably seen a movie about the man who knew infinity. Yeah. How many of you have seen the movie Man? So then you should be knowing G.H. Hardy. He was actually the supervisor of Ramanujan, right? So in his one of the mathematician's apology, he wrote this one. Both Gauss is, how many of you know Gauss? Yeah, so he's a famous mathematician, right? Can you remember any of one of his theorems or results? Okay, Gauss. So anything you don't understand in some theorems, you can say it is by Gauss. Yeah. So Gauss and lesser mathematicians may be justified in rejoicing that there is one science at any rate, and finite field at any rate, and in their own, whose very remoteness from ordinary human activity should keep it gentle and clean. Because these people were they're working on pure mathematics. Some of these concepts were, they thought, completely not of any particular application. But is it true now? So really after 40 years now you see any mundane application you do, for example paying for a pizza or even things, it happens, all these finite fields will get crunched in your mobile phones before securely it happens. So it's in a kind of so even a mathematician, so he was actually set as an apology, but it gets useful. So you don't know when your theory, mathematical theory can be useful. Yeah. This is one of the things. And also because of the Galois field becomes pretty famous in the early days of Shannon time. Shannon when he gave, and many people, mathematicians jumped onto it, and some people even wrote poems about it. So Galois fields full of flowers, primitive elements dance for hours, climbing sequentially through the trees and shouting occasional parties. So this is by Golomb, and a famous information theorist, and who he passed away a year before. So let's look at the model thing again. It's a communication model. A typical communication model should have at least the following components. For brevity, we only consider messages as sequences, which are bits in this case. So I've already introduced G of P as a major source of finite field, and most of our ideas will try to explain with that. As you can see in distributed storage code, more than code we may need to actually this algebra like doing equations with finite fields, and so that is why actually I focused on modulo P. But when it comes to that, here some basic things I think probably pretty clear to you. You have a message source of information in bits, and encoding process actually takes converting a block of k bit information into an n bit code word. Channel is a medium in which n bit code words gets sent from sender to a receiver, and decoding process is a process of converting n bit received block back into k bit message, and sync basically uses the information sent across the channel. This is the model in which you work, and you work on this one. So the model is explained with these blocks as follows, and I think pretty clear this one. So this actually somehow so in case of digital communication, there are lots of plethora of techniques doing this function. However, these techniques are affected by what's called noise or distortion. So when you have a code and the noise actually affects the communication. So the binary symmetric model is one such typical model that is used, and this is an appropriate model where the errors are truly random, and many for example this model is still useful for even satellite communication. It still some of those things it still follows more for almost model quite accurately. So in practice the noise appears more bursty, not the random thing, but however this is the when you study this you do like this. So for example in a binary symmetric channel the input is 0 and 1, the crossover probability p, which means that most of the time 1 gets delivered as 1, but with probability p there is a chance that 1 gets delivered as 0. So in that times is an error. So this is the characterization of a binary symmetric channel. Some definition for that, and now a definition of a block code. So obviously a block code is a collection of binary blocks called code words and of the same length. So example here is the block length is 4. Here there is an example, I think it comes up there, I think it's missing here. N is 4 and there are 8 code words. So nk block code is a code in which each code word is of length n, with in which k bits are information bits, and the number of parity bits is therefore n minus k. So continuing the general block codes, in general it can be defined over queries alphabet symbol. A block code of size m over an alphabet size q is a collection of m n length blocks called code words, all of the same length n. So if the same code is defined over G of q, then k symbols are independently chosen, and n minus k symbols are called parity. So totally there are q to the power of k words. So I think with the binary things we considered yesterday, with q the q can be the finite fields that we talked about it. So let us say if you have a k bit of information k and n minus k parities. So the code has a complete freedom to choose any of the G of q elements. So each of these things you have a q possibilities, and so total number of code words is q to the power of k, and in any code m is a capital M is generally you refer to the number of code words in the code, and these are parity equations depend on some of these information bit as in the previous case. So for nk block code, the rate of, so you need to have another definition called the rate of the code, which is simply the ratio between k times n. So in fact what we'll do is that parity symbols add redundancies to the code. For every k symbols of information we have n bits of code output with n greater than k. So thus in the data communication speed of the coder is not increased, the coder slows down, so the input data rate. So for example input data rate is sending at certain rate, because we are adding a lot of parities, the rate goes down. So in order to meet that, you will have to actually speed up the input data rate. So now how to compare different codes? So you should have some idea of comparing different codes. Here the main hope is that redundancy should help to remove the errors and distortion caused by the transmitted code word. So we will now introduce a concept of a distance, So how do you, so once you have a q power k elements and all the code words, there will be m code words. So m code, so another thing distinct to really keep it in mind is code is a plural, right, that it has a collection of code words. Okay, so lots of so you have a first code word, second code word, up to C capital M each code word. Each code word is of length n. So there are k bit of information, n minus k bits of parity. So parity bits, all parity bits in here depend on the information bit in some way. So what happens is that we only have a q power k different possibilities of input. When it gets transmitted, these C1s, whatever, just like the yesterday what I explained, C1 will get distorted. So there will be some errors added, and so they will be. So if you have a space of q power n different vectors in the thing, because the length is n, and the code words basically they are the special vectors inside that form to q power k, but an error happens, takes particular code word to say maybe another code word here, another vector here. So the problem of decoding is to actually come back to this one under some metric. So you need to show that, so for that some idea of a distance is needed, without which you cannot conceive this idea. So just to give you an example, here the block length, here the example comes here. So there is a block length of n equal to 5, and there are 4 code words here, and can you remember what kind of a code is it? So you can see that it is a binary code. And in fact the code words is, there are only 4 code words here. So first code word, second code word, third code word, fourth code word, 5-2, yes. So there are only, because there are only 4 code words, so only in the linear case you can actually do, but at this point of time I don't care. I capital M for the code word to be 4, and the length is 5. Okay. Now so in order to, as I told you that you need a distance, so Hamming weight of a query block is a number of non-zero elements in the block. So the Hamming weight is, this definition is very simple. So you take any vector, number of non-zero elements in it is a Hamming weight. Is that clear? Yeah, just this definition. That is, take a vector, and the weight of a vector is basically counting the number of non-zero, right? So this is often, sometimes lots of variations and things are done in this area, in this one. So for example, let's take modulo 7, in the modulo 7 example. So you have some vector given by 3, 7, 0, 0, 4, 2 of length 6. Okay. What's the Hamming weight of this vector? So number of positions that differ, right? 1, 2, 3, 4. That's the weight of the vector. Okay. So the Hamming weight, the Hamming distance between any 2 Q array blocks of same length is the number of places in which they differ. So that's the general definition of Hamming weight, which, where for example, an example we could do, let's call this as A. Pardon?
7 in marks.
Okay, so that's a good question. Yeah. So then what this would be actually? So what's the that's why what is the Hamming weight now?
3.
Yeah, 3. Exactly. That's good. actually 7 is 0, so actually Hamming weight is 3. Okay. So if you have another one which is 3 1 2 0 3 1, so another vector A B. So Hamming distance between A and B is the number of positions that differ. Okay. How much in this case? So the number of positions that differ, here the match, differ, differ, match, differ, differ, so 4. Okay. I'm actually giving an example here over a bigger alphabet, which is Z7, but in case of binary blocks, the distance between two binary blocks is given by let us say you have a 2 box, the distance between A to B is same as the weight of exclusive or sum of these 2 vectors. So can you prove this result yourself? So given a binary, given 2 binary vectors of length n, A, B, the Hamming weight of between the AB is same as the number of exclusive weight of the Hamming weight of the exclusive summer of A and B. So by applying the definition of exclusive OR, so let us say A exclusive OR B equal to 1 if and only if one of them is 0, right. So which means that and also A exclusive OR B is equal to 0 if both of them are same. Okay. So which means that picks up exactly right. So obviously the theorem you can prove for vector of length 1. Okay. Now once this is what's called a mathematical induction, then you can show that for a small length n, if the theorem proves for up to length n, then you can use this little extra to related to n plus 1, and using a mathematical induction you can prove. But idea is very clear, right? The number of this one is, this portion is clear. So but this will be quite handy, because in the other case is a Hamming distance, the number of positions that differ. In other case, what you do is you take an exclusive OR sum and find a weight. Now you can also generalize this result to this. What could be the result here? Can you write now the distance between A and B to this one when it is defined R? How do you define this one? Can you extend it to general finite field now? For a binary field I have given there. Any idea? So I can do the modulo 7 arithmetic. So I have a Hamming weight of a Q array block is defined. So Hamming weight. So let us say Hamming weight of, that's defined by H. What should be gone here? Very good. A minus B, where minus is defined as a pointwise subtraction operation modulo 7. Okay. So which means that if you have a particular one, A minus B is 0 if and only if both of them are equal, otherwise it will be non-equal, right. So by taking 2 vectors and taking pointwise subtraction between them, then you only count the number of non-zero position, that gives you the Hamming weight. Okay. So Hamming weight of for example in this one, Hamming weight of this is same as another vector. 3 minus 3 is 0, 0 minus 1 is minus 1, 6, 0 minus 2 is minus 2, 5, 0 0, and 4 minus 3 is 1, 2 minus 1 is 1. So you can see that the Hamming weight in this case 1 2 3 4, and that's what we got answer, right. So this is a very useful idea. That means if finding Hamming distance between 2 vectors, I can actually exclusive OR and get that result automatically. And in case of binary, it is the subtraction is same as taking exclusive OR. So plus and 1, you know, it remains the same. So 1 plus 1 is 0 in exclusive OR, right. So everybody is clear about exclusive OR function? Yeah, I think there is no issue with that. So with that, so this is a very useful an idea, and most of the time that has been used in many places, you know, it comes very handy. Okay. So listen, I already have an example here with the binaries, that is why I gave an example over GF7 there. So you got an example, A is a block of here 3, 6, 7, and B is there. So you do exclusive OR. So obviously you can say 1 plus 1. If they match, the exclusive OR functions will give you 0. If they mismatch, it will give you 1. So that helps you, also another way to do it. So really you can have a proper proof, and you know, that's how you do a proper proofs on these ones. Now a concept of you know, because when we have a NK code, what we do is that the code is basically a some subset of n length vectors having you know, whose size is almost equivalent to 2 to the power of k or q to the power of k maybe, and they gets spread out in a bigger space which is of length n, and I want to find out actually how good they are, which means that I need to find out about their properties with respect to how they are separated in this space. So we would like every code word to be as far as possible from other code words, because it is the errors that take one code word into another vector which is not the code word. But if too many errors happen, it may be possible that one code word exactly becomes another code word, and we will not be able to actually identify that. So if the distortion is too much that one code word becomes another code word, at the receiver we will not be able to distinguish whether what was transmitted. So we want to somehow arrive at it, how many errors that our system can guarantee, can trick, which means that the distortion should be just enough so that we will be able to distinguish properly. So then we will not be able to, we will be able to say, okay, this is better than the other one. That means you should be able to restrict, you should be able to analyze the properties of this for our application. So the idea was the idea of a minimum Hamming distance of a code is a minimum Hamming distance between all pairs of code words in a code. So you have a C1, C2, C3, C4, C5 up to CM, capital M, all of them, and I want to find out, say, the distance between every, like that, and similarly with every other thing. So there are totally M is a q power 1. I want to find out the mutual Hamming distance, and I want to find out the minimum, because that's the minimum, you know, that will tell me the performance of the code. Because if the number of distortions happen exceeds the minimum 1, then we will not be able to guarantee whether error happened or not. So we need to understand the minimum. That's why minimum Hamming distance becomes important. I will explain the more consequences of that in short time. But look, you could see that the complexity of determining this is going through, just if it's not a code word, I have to go through m times m minus 1 by 2. It's a pretty, is that clear idea? That is that I need to find out with every other one. So obviously this distance function is a metric. So distance between vector and with itself is 0, yeah, and distance between A and B is same as distance between B and A, yeah, the symmetric property which you can prove it easily. Then there is the other portion which is called the triangle and inequality, is that runs as follows. So the distance between if there are points, you know, for example A, B, C, that is the distance between A to C is always less than or equal to going to distance between A to another point and distance from B to C. This is called a triangular inequality. That actually helps you actually to find out the minimum distance directly in any plane. So for example, you know, when you have a Euclidean plane, the triangle inequality always holds true. So any distance function will have this property. Can you prove this with this one? using, can you prove the above relation? So here the proof goes as follows. So what we did was in the past we proved that distance between A to B is same as the weight of the vector with A plus B, A exclusive or B, right? We proved that. Yeah. Now let x, y be two n length binary vectors, and then we have, you can take w of weight of x plus w of weight of y is always greater than or equal to weight of exclusive or y. Okay. Now consider weight of x, A exclusive or B, and weight of B exclusive or C. These are two vectors. Now what is this value? This has to be, this is x and this is y. The weight of these two is always greater than or equal to weight of the exclusive or of this. Whereas the exclusive or of all of this, B exclusive or B is 0. This is actually weight of exclusive of AC, which is basically the distance of AC. So by just using this function, I can prove that now the distance, this is inequality. So this gives a firm footing. For example, if the number of the Hamming errors happen, we will be able to distinguish, for example, one code word has gone into another code word or not based on this value. So you get a proper footing for the distance function. Is that clear? Yeah. No issues, right? This one. So now we need to definition about error detecting capability of a code is a maximum number of errors that can occur in a transmitted code word that will always be, enable the receiver to detect the error. So I want to find out the detecting capability is a maximum number of errors that can occur in a transmitted code word that will always be enable the receiver to detect the error. So you can say that the minimum Hamming distance we found, let us say, if a code is d min, then the result, we are going to do a simple result which says that errors are not detected in a received message if and only if the error vector itself is a code word. Okay, only when then, because any other situation, if we have something, let us say all the C1 to Cn is there right here, C1 to Cn, and if we can always detect if the error vector is not itself another code word. So any other code word, if it is there, I can detect it. So that's the kind of logic you use, and the error detection capability of a code is always one less than the minimum distance, because sometimes with the minimum distance, which means that that many errors, it can turn one code word into another code word. So that times you will not be able to detect that error. So so that's why error detection capability of error is actually one less than the minimum distance of the code word. So now, so that's clear. So that's what error correction capability of a code is a maximum number of errors that can occur in a transmitted code words, while always remaining possible for the receiver to recover from the error from the original message. So let's look at, for an example here, a code word, code with two code words. One is depicted here, which is about length 8. It has two code word here, and if the received word is this, which is 3 plus 6 0, 6 ones and 0, and given fact that there were two errors, you cannot determine whether the transmitted code word is C1 or C2. Clear? Can you see? So this particular example is lead to see. For example, here you can see that the first code one, there are only two code words. So the C1 and C2. Okay, is I won't even come back to linear code at all. So just I'm just looking at a code, this kind of thing. So what's the distance between C1 and C2? 4. And now the receiver things happen to be this, right? So, but can you detect this error? So can you, obviously what has been received is not one of these two code words, so we can easily say that, so we can do so. Here there are only two errors have happened. So if the two errors happened here, how two errors could have happened? Two errors could have happened from C2, For example, the last 2 bits, if they turn it to 1 1, then so that means the received word is at a distance 2 from this code word. Then we look at the other one. What is this? So this is also at a received 2 1. So that the received word is now at the same distance between these 2 code words, then you will not be able to distinguish which one was transmitted, right. So that means 2 errors, this cannot correct. Now how to actually characterize this better? So obviously this means that at this point when you get such an example, I can precisely say that the error correcting capability has to be strictly less than 2, so it can't be 2. So we could not decide, and in this case it can only detect 1 error, not 2. So how can we correct errors? So what is the limit on the number of errors that can be corrected? So let us see with the transmitted code word, R is the received word. So just in the continuing with our previous things, now R can be C exclusive or E, where E is the error word. So the effect of error is that it increases the having distance between the code word and the received word. So in error correction, we choose a most likely code word nearest to the received word. The having distance we defined earlier defines that nearness. So that is why do you know, when a correction, we would like to find out which is the most likely the code word that is nearer to the received word. So one of the ways we could do is that take a received word and find out the distance between all the code words and choose the one with the minimum. That should be a reasonable guess that was the thing. Right. But we need to want to surely say that is actually the idea of decoding. So let us consider with an example 4 where the block length is 5 and the number of code words is 4. So here is the this code word n equal to 4 and the number of code words is 4. This was we considered before. And this code, can you recognize this code? It was before, what is the K here? 2. So we describe 2 different decoding situations. In the first case, in the figure 3, so let's come here. So there are, in the first case here, so there are 2 this here. So the number of the received word is basically 111. So what was the thing, received word? Okay, so this is the received word is all 11, and we look at the each code word C1, C2, C3, C4, and we have actually computed all the vectors which are at a distance 1 around each of these code word. So for example here 0, so all these vectors are at a distance 1. This is C2, this is C2, this is at a distance 1, 1, 1. So there are 5 different possibilities. So there is totally how many vectors are there? So there is 5, 3 plus 2, 6, 12, 18, 24. But how many vectors are there of length 5? 32. So obviously there are some more vectors which are somewhere in between. Yeah, we don't know. But that is why this code is not a perfect code. Yeah. So that this is an example of a non-perfect code, but assume that the received word is 1 by 1 and you identify that so that's actually belong to this one. So if you compute the distance between say C1 is 4, C2 is 2 and C3 is 2, so you can see that this has only 1. Okay. So obviously by choosing this way the decoding will be unambiguous, and assuming that maybe single error is most likely have occurred, because obviously the probability of 1 error happening is much higher than probability of 2 error happening or even probability of 4 error happening. So you could actually you can decode it. This is an example of an unambiguous decoding. But on the other hand, receiver happened to be something like 10001, okay, and in this case this particular vector falls outside the unit spheres of all the code words, and you could easily compute now this vector is at a distance 2 from these 2 code words and distance 3 from these 2 code words. So this is here it is impossible to correct errors, but we can say that something bad has happened. Yeah. So this is the idea of both error correction and error things. So now that comes to our next thing is basically what's the precise definition of error correction or the measure of error correction. Error correction is possible only if the number of errors is less than half the Hamming distance of the code, because this will ensure that an erroneous received message will be closer to the transmitted code word than any other code word in the code. So you can say that result error correcting capability of the code is always d min minus 1 by 2 divided by 2, where x denotes the integer part of x. Okay, so if you do that much of things we can always correct, and the d min by 2 is defined as error correction capability. So you can actually try proving this, and some of these proofs will come as we go through the other idea, higher ideas. So some primary problems in coding theory. So primary goal in coding theory is given code length n and minimum distance d min and a code alphabet size q, you have to find code C of the largest possible number of code words. A related goal is that given a code length n and given an alphabet size q and of size m q power k for k less than n, find the code C with the largest possible minimum distance. So sometimes given the values of n and k, you find a code with the largest minimum distance and so forth. These are the two, generally these are the primary problems. There are many. So from now onwards we assume that the alphabet size is a finite field is order of q, and q is now I haven't defined the primary finite field of size, which is power of a prime number, which we will discuss in the next class or in the coming days. But at the moment you can assume, for example, we have covered for m equal to 1, we have a finite field, and that's how the linear codes are chosen. Okay, so that this covers the basics of intro. So if you have any questions, we will continue, and I'll be there for some time.
What does GF2 exactly is?
GF2, so Galois field. So finite field, Galois field, finite field, they are all same objects. Okay. Now GF2 is elements having two elements. The way the prime used, the same the alphabet I choose, where p is prime equal to 2, then what you get is GF2.
So where is the fieldness in this definition?
Okay, so the question is, where is the fieldness in the definition? So this is what I went through the numbers modulo precisely for that reason. In fact, even after some people give you I'll give you an axiomatic definition of a finite field in the next class, in the next definition. But main idea is that what is the fieldness of the field? Field means I haven't fully defined things. That's what you've been telling. But what I showed you was that we defined element called ZP, all modulo prime numbers. Now what I am saying, we show that you can be added, any two elements in this can be added, then it becomes in the same field. Now what we looked at is all the numbers less than p, that is 1, 2 up to p minus 1, which is they are less than p, they never divide p, so they are all relatively prime numbers. No, 0 will divide p. So I'll take out all the other. Of course you can't multiply, and so you can't find another element with 0 multiply by something you get 1. Okay, that's not possible. Other than 0, what I showed you was using the extended GCD algorithm, that you can always find an inverse of an element. So that means that all other elements other than 0 can be inverted. Now this is a field, and mathematically what is a field? We go back and in axiomatic form we will say that the field has a structure with two operations, and that's been done. That's what you see in textbook. Okay, most of the textbook. What I thought is that instead of doing in that format, which will I do little bit later, but I give you an example of a field which was modulo p and the prime number. Yeah.
Those 7 properties need to be followed.
Yeah, so I'll come back to that, but don't worry about for checking all those things. I want everybody, come from different background. We want to feel about what is finite field much easily. Okay, and then we will patch up a little bit and come back. Okay.
So my concern is to feel the fieldness in the definition of the field and the ringness in the definition of the ring. Still, I am unable to perceive that how a ring looks like. Is really a ring kind of the structure, or
so okay, I mean just now I didn't want to be I wanted to start from a gentle coding theory point into a little more gentle here and move on to. So today we looked at the numbers and we constructed numbers that has a properties of like a field, and I told you that G of P is a field. Okay. Now we will come back and we need actually for most of our application we need G of P to the power of something which requires a much higher concept. Will come to another day. Okay. But the fields and rings and they are all definitions, okay, done with some with some properties associated with it. We will define that. That's the definitions. And in this case, so you can say that every ring is also a field. So what you do is that basically when you have two operations, if both are closed under that will become a ring easily. But when all the non-zero elements has inverses, then that will be a field. And there are some cases in ring not all elements can have inverses, some are zero divisors. So in Galois field all elements have inverses, and so the example that I depicted today with ZP, and I even give an algorithm how to do that. For example, going an extended GCD algorithm and find out the inverses. So that means that I can divide elements in it. So I thought that should be enough as a first example, but your actual definition of a field and everything will give you probably before I go to RS codes that is needed, because then we need to manipulate those symbols to see and then extend it to other codes. So this has been is not a very comprehensive coding course we planned, but what we want is that even if somebody who has not gone through basic mathematics, you should be able to kind of appreciate what is this P is about. Yeah. So for example, at the end of the day, when after you making all this finite field in case of array and others, you use only G of 2 power 16, G for 2 power 8, G power 16, 2 power 32. So why should we learn all of this? But the idea is that you only when you formulate a problem in a general finite field and look at it, then you will see the other issues, the theoretical part. But when you then in engineering part we will decide, okay, there may be other codes possible, but what best works in practice is working with binary field. Yeah. So for example, G of 2 power some 8 and 16, they are all over binary, but extended as a polynomial. So I'll actually describe them in a much simpler way using polynomials. So at the moment we used the integers which were given to us, like something that is available already, and then we make some mathematics out of it, and we looked at it today. So the purpose of today is just to get that thing automatically, but recognizing that this is an abstract finite field having these properties, then you need to know the definition of a group, a ring, and so forth. So I think they are important for its own sake, but I think what is more important is to actually have a direct grasp about the structure that we took. So that's why we did with this. So I mean, since I also give you an example through Magma, you can work out, for example, a finite field of size other modulo 11 yourself and run through the things and construct the addition and multiplication tables. So you can choose 0 1 2 like that, 0 1 whatever that you want, P minus 1, and okay, and the idea is that with the addition everything will be there. So each row will be permutation of each other. So it will be 0 1 2 up to P minus 1, we 1 2 up to P minus 1, and this will be 0 and so forth. Yeah, with multiplication except 0 and 1, every row will have only 1 at one place only. So that actually helps you to get the inverse. So if it is not a field, then you will see some zeros here that will not be used for things. So what kind of a rings will have 0 here, how many zeros are there, then it will become much more technical and more depth in the thing. But for our application, so for using erasure codes and others, what we need is G of P power m okay, prime to the power of m, and mostly we use p equal to 2, but you know, in general that's the structure that we are going to use, okay. So you see the thing, I want to fully answered all the things in fieldness and ringness. For that basically you need one full abstract mathematics course, but I want everyone, you know, who come from computer science background, other background, engineering background, to have a feel of these numbers. So once we know that what we are talking about it, then you understand, you know, there won't be any mysticism associated with it. Oh, what I am talking is only a numbers modulo prime number, nothing more, because you know, what we are actually handling is only residues of dividing that, and so that's why this division is an important idea. As I told you, just with the simple concepts, there are many unsolved problems in number theory as well. So you know, in fact you can say that this is the foundation for the rest of the algebra to come up, and that was one it is, has been there. Okay. That question? Yeah. Any other question? So
when you measure distance between two vectors in GFP,
how,
magnitude also matters. So you have told it as only the number of questions they differ.
yeah. So I mean, when so I gave an example of Hamming distance. So the distance is basically number of things, how they differ. How much they vary and different, like that requires another metric. So for example, if you're using a phase modulation, you know, for example, all these symbols gets modulated, the phase of a high frequency signal. So you have a high frequency signal, they're a real signal. So the problem, all this confusion comes because of the you know, so let us say this high frequency signals, and and its phase, like, sorry, maybe this is not a good picture, you can signal like that, you know. So you can start something with this phase, and the other phase you may start like this, and the other one is like this, which is the, you know, changing the phase, and depending on the number of phase you change, that time we need to be careful about the, you know, the distance. So that time we may use Euclidean distance, that is mapping G of P back to the real number, and then you actually do your algebra over it. So that time the distance things are different. But the interesting thing about, say for example, binary one, if you do, sometimes you use sin omega t and cos omega t. And any distance measurement you do with that one, slightly, you know, the carries over with Hamming distance would be good enough to do that, you can do. So what we define distance is over G of P. How that gets used in practice is not our comes at this point. You know, in case of storage, you know, we directly map elements to this. So the concerning distance would be mainly the Hamming distance would be there, because if I have stored this and I see something else, means I don't like it, right? That's what. So really the distance I need is the positions where they differ is a metric, that is. So what kind of a metric you require for application, that depends on it. So symbols can be used in many ways. So most of the time all the definitions is you know, in that sense. Okay. So but what I am saying is that I explained, for example, the proof of the given two elements A, B, have A and B and C. So the distance between A, B plus distance between B and C is always greater than or equal to distance between A and C. Right, the triangle inequality, and by using just the Hamming weight, you could get it, because the weight is a you know, the function, very easy. You got that proof very easily because by choosing x and y, right? Now, how do you prove the same triangle inequality if A, B, C are G of P vectors, like a general non-zero vectors? How do you prove? That's the thing you should. It's an interesting question. Then I can't apply exclusive OR, right? But I told you that again. I told you that, let us say, this is the general thing. So distance between A and B is same as having weight of A minus B. Yeah, this is true. So I can now convert a distance between any two vectors to a sum vector which is basically obtained by pointwise exclusive pointwise subtraction, and I can just compute the weight. So I have simplified, right? So how do you now prove the triangle inequality with this definition? Pardon?
It will be on the similar lines. I mean, it will be A minus B minus of B minus C. We calculate the weights of A minus B as one vector and the weight of B minus C as the other vector. Then the weight of A minus B plus weight of B minus C will always be greater than equals to, less than equals to.
So you write down the steps and see whether you can. So with respect to Hamming weight with the exclusive OR function, that because of that weight function it become easy. But here this is not true. It's not straightforward. You probably need to do a bit more. So basically, Hamming distance tells you that so let us say A goes to B. The distance is actually a number of positions that differ. B goes to C, the distance number of goes to C for. So the distance between A and C basically has to be greater than, because there could be some positions where from A to B and B to C, if they remain, if they have a same number, then that won't get accounted in this, but it will get accounted there. So it will be more always. But in order to precisely prove what you have to do, you have to actually come up with some kind of a proof idea. What you do is that, okay, when I take two vectors together, I can put into the set of all, I can know the positions where they differ. These positions are actually a number between 1 to n, right? Positions are between 1 to n, and I can collect as a set. Okay, so if I have A and B, I can find out the number of positions that differ, put them in one set. Let that be the set of all positions where A and B differ, and you put another set with the positions from B to C is differ. Now you have an algebra with the sets, and you can see that the union of these two sets will be the distance between these two, and then you can look at the intersection, and using set theoretic ideas you can follow the same proof. And it's a little bit working has to do, but that's what you do thing. But let's say for most of our purposes, if you appreciate the proof that I gave you, that the weight of by using exclusive OR, that will be good. So you can see that the complexity of proofs can go can increase very easily depending on where to start, because with the proof basically what you do, you start with the basic axioms and then you keep on continuing. The idea, what you need to is that you need to do properly, that should ensure all the correctness of that they can say. Okay, is that, yeah? So I think I think for all the storage code thing, the main metric that we use is Hamming metric is enough, because that's where, so you store something, and if you don't say read the same thing, that's an error, right? This is what we do, and in most of the cases, as I mentioned yesterday, erasure things are more important, because we know which part is not there in the code. Yeah, so we could actually do much more with the erasure. Yeah. So I think as a task, you take the second set of slides that I given for the extended Euclidean algorithm, why the extended Euclidean algorithm converges, and hence the GCD found in the extended GCD algorithm can be written as linear sum of the input variables. Okay, and I can easily obtain them. Why it is possible, all that proof that I have given in the thing. So if somebody goes through it, and if you have any questions with that proof, we can do. Otherwise, I can go through another sitting and just explain to you why the proof works. And that's a pretty interesting proof. This one, and they are the basis for many things. For example, when we do VCH code and Reed-Solomon code, some aspects of the decoding actually involves this extended Euclidean algorithm. Yeah, so that's an interesting thing, but now it has become quite these topics have been quite standard, and so they have not been discussed in coding theory circles anymore, because one of the things that happened is all these algorithms can be easily implemented. Remember, in the early days of coding theory, even encoding matrices and others, there were papers and lots of books were written, because that was a problem then. But now, as computing has evolved, many polynomial time algorithms are actually implemented pretty efficiently, and most of them available as a as a add-on. Maybe functions are available in the processor itself, or or maybe you could memory map it, the whole thing. So, for example, finite field operations are completely given as a tables in the distributed storage. For example, the things that RAID that Aaron mentioned today, there are some RAIDs will use some kind of a parity, some additional parities, but all of them are computed more efficiently by using the memory, maps everything already put into it. So, you do not try to compute with algorithm. But why do we then have to do it? If you have to really understand the thing, so you need to first do once properly, and finally after doing all of this extended Euclidean algorithm, I am not going to actually implement it. I will probably do a table lookup method and complete my implementation. Yeah.
Suppose all this work is done if received and transmitted vectors are same length.
Yeah.
What if a vector delete
Yeah.
during transmission? Then what option do we have?
So, very good question actually. So, there is a whole lot of a new area of coding theory, which is called insertion and deletion codes. So, the codes that can detect insertion and deletion errors.
So what kind of distance will work in this scenario?
There is a fair range of things. The one which that comes to my mind is in computer science, when you search for something and people do with the minimum errors, what's that this is, for example, in Google, you search something and obviously you will try to look for a word which is at a nearest distance, edit distance. So, there is edit distance. So, in case of computer science circle, that is what comes to my mind quickly, but there are other channels that can have this insertion deletions ones, and in the olden days in my when working in the company, we were thinking, mostly they are all mentioned by sequences with good correlation properties to actually synchronize. So, if the insertion deletions are there, then our synchronization will pick it up and do it, but to have a code which corrects that is a pretty detailed mathematics things, and it's a very niche area, small area which is very detailed. And there are lots of even now there are some good papers coming in those areas. You have to go. It's a very good question, but that's out of scope for this. And even most communication engineers also don't do it. Don't worry about that one. But I think the most popular one is edit distance, that's been used in Google searches and stuff. So, I have two more set of slides for finite fields. That is the one is on the question that you asked, ring and field and groove. So, traditionally in coding theories, people will start the definition using ring, group, and they start developing it. But it's very hard for people to follow, because these are all abstract concepts. You don't have something in concrete in mind to associate with. So, the purpose of today, the introducing numbers, is precisely for that purpose, because the numbers is pretty basic, that everyone can associate. And so obviously using this we can so by looking at the workings behind these numbers, we can feel why the mathematicians would have come up with the idea of a group there, why he comes up with an idea of a field and ring. You can understand, because these are there, these numbers, whatever there is there, it is not that you create, it is already there, just like other things are there, like things outside what you see out, just numbers are also there. So that's a kind of a it's that's what I mean. The numbers actually is good. It can become more philosophical as well. So by understanding them and then and following especially those structures that are nearer to our case, then we will oh we did that one and this is a field here. So when other people refer to this field, this is the definition they use. So now I know, I had to just think about it as a prime number and I had to divide and take the remainder. So this is I've been teaching some of these ideas in a cryptography class in a big way. It's been very difficult for people to appreciate that idea that what we are playing with the residues, not the numbers. So when I say in GF7 whatever, say 6 there, that 6 and the number 6 is completely different. That 6 is actually obtained, a residue obtained by dividing by prime number 7, then that is 6, and that is, and in fact 6 can be represented as -1. So I didn't come back to some examples. Say with modulo 7, 6 is -1. So by recognizing, so actually another thing that I would have probably done is modulo 7 is based like actually clock arithmetic. You can think of a clock arithmetic here. So this is 0, 1, 2 like that. Let us say this is 10 and 11 is 0 again. It's a clock arithmetic. Okay, and you can actually move move both way. So if you want to go from 0, -1, -2, you can count this way, or +1, +2 in the other side. So if you understand the clock, how clock works, the numbers that we associate with is actually the numbers in the clock, like that. So that's okay. That's another way we want to do, and we want to precisely say what they are. So if the modulo is a prime number, then it's a field. If it is not a prime number, then it's a ring. So what happens is it takes Z4. Okay. Now 0, 1, 2, 3, and I take everything is modulo 4. Now you can see that 2 in Z4 divides 4. So that you can just say 2 times 2 is 4, which is 0. That means 2 non-zero elements, when multiplied becomes 0. Okay. So that alphabet is a ring alphabet, and for example when this is used in conjunction with phase modulation, like 4-phase modulation, then you can actually get like for example a CDMA communication system uses these kind of 4-phase signals, and the distance there is a Lie distance. That means the distance, for example here when you are coming from here. So what's the minimum number of steps? So let us say this is the point, this is another point. The distance is defined as the either the number of steps going from this way or that way. So the minimum number of steps on this clock, either this way or that way, that is the Lie distance. So for example here 1 and 10, with the normal, if you take just 1, it will be 9. Difference is 9. But along modulo 11, this is only 2. Because 1 minus 10 this one will only, the difference is only 2. So that is a Lie distance. So that distance can be is useful in other applications. So depending on the applications, you have different distance. But the one thing that you notice, you give attention to is that, why is this a distance? That means it should have a triangle inequality. You need to have a proof that what we have similar to that. So that's how you actually capture knowledge and understand more. Yeah? So for some of these applications, we just use only the Hamming distance. So for all this course, it's only Hamming distance. But it's good that the general questions actually help you to see what we are. Okay. So today we just did the finite field, and then we also introduced about the issues happening with the throughput and the delay, and especially because of the performance in distributed systems, because finally we are going to use them in that one. And then we looked at the basics of coding through some examples. We cut short because it is not a formal coding type of approach, but the main emphasis is to get the concepts pretty quickly, what is n, k and distance and the error correcting capability and error detecting capability. I hope these ideas you should be able to kind of prove and some things. I appreciate that. Any other questions? Yeah, okay. Thank you.